Hello, my name is Lauren Kim, and I'm going to be discussing the physics lab of constant velocity. Um, so I'm going to start with the purpose. The first goal in this lab is to observe the motion of an object with constant velocity and without any change in direction, meaning a constant magnitude, meaning that in my case, it would be a constant positive slope. My second goal is to compare the experimental and computational models of the movement of a car when pushed on a track. So seeing how a system calculates it versus how I calculate it versus from what I've observed. So there's two different systems I'm using. There's the experimental, which is directly what I see in the movement, and then there's computational, which is using a system called GlowScript to model what I am hoping to achieve with the experiment. So I'm going to start by saying that there are some assumptions I have to make in this experiment to be able to discuss anything. And first of all, I'm going to assume there's no friction, no air resistance, and there's no error upon pushing the car. In addition, I have to assume that displacement only changes with one axis, meaning that the y and x axis don't change upon my pushing, and the only forces acting on the car are the forces of normal force and the force of gravity, as seen on the chart over here. When the diagram is first pushed, there is going to be a force there, but we're going to assume that the normal force equals the force of gravity, meaning that there is no net force on the car. So it's good to back up my data with the principles that I'm using in this experiment. The first one would be Newton's first law, which is the law of inertia, meaning that an object can remain in motion without being acted on by an external force. And to add on to this, if an object is at rest, it will stay at rest. And if an object's in constant motion, it'll stay in constant motion unless it is acted on by an external force. In addition, I'll be using Newton's second law, which is force is equal to mass times acceleration. Force is equivalent to the change in momentum, which is mass times velocity over the change in time. These were the two main formulas I will be using, which is the change in velocity formula and change in position formula. In the change in velocity formula, I am assuming that the acceleration is equal to the net force over mass, which is why it cancels out because the net force is equal to 0 in this experiment. Now, to set up the experiment, I have to explain the system and the surroundings. The system of the experiment will be the car and the track that it's moving on, as seen in this image over here. And the surroundings is anything around the system, which would be gravity, applied force, just basically anything that could affect the system. Now I'll be playing the video. For the tracker, I just pushed it and then I added the center of it as it kept moving, which is how I collected my data. And it was just straight pushed on a track. So now it's time to analyze the actual data that I got from the tracker. I didn't put all of it because it's around 51 points, so trying to put it all on the frame would be crazy, but I put the first two so that I could show you how I found the initial velocity. So to calculate the initial velocity, I did the change in time from the initial time to the second, and then I also did the change in the position, which would give me my initial velocity, which I then used into my GlowScript, which I put into the ball's velocity as the first one for x. And that's how the system was able to calculate what the initial velocity had to be. So here's the actual calculation here. These are things I changed. The first thing I changed was saying that the net force has a vector of 0, 0, 0, which is basically saying that there is no net force, which is why I can account for constant velocity in the system. In addition, I added the change in velocity and change in position formulas so that the system would be able to distinguish the momentum, like Newton's second law, and calculate it there and get to that point of velocity. So here is my observed tracker versus predicted. So my observed versus predicted chart, which is position versus time. And as you can see, there was a little bit of a difference between my two lines. And I think the reasoning behind that is that there are forces acting on the car that I could not control, like friction and other things that I just could not account for. Like when I'm pushing it, I just can't stop it from accelerating if I push it too hard, something like that. Which is why in the beginning over here, it seems to be the same, but it slowly skews off because GlowScript is like accurate. It's like fully made to be perfect velocity, while what I did was gonna have some human error. So in terms of the discussion questions, what if the axes were flipped? All it is basically saying that the velocity vector points the other way, and as you can see, the distance traveled remains the same, but the slope is now negative. In terms of how many push or pulls, it is nearly impossible to find the exact number of pushes or pulls that'll contribute to a net force of 0. And the reason that assumptions have to be made prior to the experiment is because no matter how perfectly I push the car, there's just no way I can prevent friction, and there's no way I can prevent air resistance or anything against that track. So there was going to be some form of acceleration or maybe deceleration. The predicted model achieves constant velocity because the computational system of GlowScript does not need to account for the friction or acceleration. It's just literally the perfect model. Now, in terms of potential errors, I have been talking about before, but there is human error, which means I could have had a more strength in my push, which could potentially lead to increasing velocity rather than constant. And of course, there's the option of like incorrect input into tractor because I had to find the center of the car every single input. As you can see here, they're not like all perfectly on the line. Thank you.